Okay. Welcome, everyone. This is, I think, the 76th meeting of New Directions in Group 3 and Triangulated Categories. Today, our speaker is Yann Palu, and he'll be talking to us about zero-slander extriangulated categories.
Thank you very much, Rajadip, for the invitation to speak. I'll try and share. Yes. Okay. Is it okay? Is it sharing correctly? Yeah, good. So I'm going to talk about some results on zero half-Slander extriangulated categories. And sorry. Yeah. So this is results obtained in collaboration with Xin Fang, Mikhail Gorsky, Pierre-Guy Plamondon, and Matthew Pressland. But it also has strong intersections with work by Dong Yang, that's still in preparation, and also results by Xiaofa Chen on zero half-Slander correspondence. So I'm sorry for the misspelling in the abstract. So it should have been Xiaofa Chen. Okay. So the whole project.
Your video went away. Yann.
Sorry?
Your video went away.
Oh, okay.
Yeah, now it's fine. Now it's fine.
Is it better here?
No, it's fine. Yeah.
So I can't hide it, right? Okay. Sorry, technical issue. Is it better like that? Is it okay?
So in the upper right corner, there is this square. Yeah. If you put your finger on that square, and yeah, that's good. Okay.
And the video still works.
The video is gone now, but I guess it's fine. No, we can.
Okay, sorry.
We can follow. We can follow.
Okay. Okay. So the project comes from two different ideas spliced together. The first one is a result due to Brüssler and Young that I will explain now. And the second one is the appearance of zero half-Slander extriangulated categories. So I'll start with two examples in order to explain the result by Brüssler-Young in easy cases. So this repetitive diagram here is the AR quiver of the bounded derived category of a quiver of type A3. And if you don't know what an half-Slander right-hand quiver is, it's a sort of description of the category by generators and relations. And here, the vertices of that quiver are the indecomposable objects, in that case, in the bounded derived category of the A3. And the morphisms between two indecomposables are linear combinations of path in that quiver, subject to the so-called mesh relations, which say here that a width square commutes, and the triangles that are at the boundary composed to zero. So the example we want to look at are not this bounded derived category, but an orbit category of it that's obtained by gluing this infinite strip along a Möbius strip. So you glue the circled arrows on each other, respecting the orientation of the arrows. So this cluster category has been introduced by Brandmarsh, Reinecke, Rayton, and Tudroff in order to categorify cluster algebras. And they were shown to be triangulated by Bernard Keller. So that's the example of interest here. And because they categorify cluster algebras, the cluster categories come with some specific objects that are called cluster tilting objects. They correspond to the clusters in the cluster algebra. And well, you don't need to know anything about cluster algebras to follow this talk, and I will define cluster tilting objects a bit later. But let's say they are interesting objects in that category. And here's an example of a cluster tilting object. So it's the direct sum of T1 plus T2 plus T3. And I repeat I repeated T1 and T3, but they're glued to the first copies of T1 and T3. So this is a cluster tilting object. And we can read the Gabriel quiver of its endomorphism algebra from this AR quiver by looking at the arrows or the path between the summands T1, T2, and T3. So there's a path here from T1 to T3 that does not factor through T2. So that's going to give an arrow in the Gabriel quiver. And for the similar reasons, we have an arrow here and here, and then it repeats itself. We can also read the relations by using the mesh relations. The square commutes and compositions below compose to 0. So those two arrows will compose to 0. And for symmetric reasons, the other will also compose to 0. So the endomorphism algebra of this specific cluster tilting object is given by a 3-cycle with radical square 0. And it turns out that this cluster category here is equivalent as an additive category to a full subcategory of the bounded homotopy category of projective objects, of projective modules over the endomorphism algebra of T, T1 plus T2 plus T3. And this full subcategory is the category of 2-term complexes. So they are the complexes of projectives that are concentrated in degrees 0 and -1. So that's denoted K brackets -1, 0. So this phenomenon is quite surprising because the cluster category is triangulated, but this 2-term category, K -1, 0, is only a full subcategory of a triangulated category. So this additive equivalence is quite surprising from that perspective. And well, we would like to know if how general it can be. So let's look at a second example of a cluster tilting object with mutated one summand. So we now replace T2 by this new T2 prime, and the cluster tilting object T prime is T1 plus T2 prime plus T3. And again, we can read its Gabriel quiver, which is of a quiver of type A3 with linear orientation. Now, if we look at the full subcategory of KB proj A3, formed by the complexes that are concentrated in degrees 0 and -1, we obtain a category whose slender rate and quiver is this one, and it doesn't look like the cluster category anymore. So the cluster category is here. However, it's not that far from looking like the cluster category. So we can see that part that changed color. It's in orange now. That corresponds to the AR quiver of the category of 2-term complexes. And what goes wrong are those arrows here. The 4 arrows here are not in the AR quiver of K -1, 0 proj A3, but we can kill them. And if we erase them, then we get the homotopy category of 2-term complexes. So this gives now a slightly different equivalence of additive categories. So we have to kill, so starting from the cluster category of type A3, we first kill all morphisms that factor through sigma at T prime, then at T, and we obtain the category of 2-term complexes. So now we had to kill some morphisms, and that's the general situation that was studied by Brüssler and Young. So we can now work with any acyclic quiver, so a quiver with no oriented cycles. And the cluster category is going to be an orbit category of its bounded derived category, DBKQ. And we take the orbits by the autoequivalence, given by the Serre functor composed with the -2 shifts. So this is, So the objects of the cluster category can be thought of as the orbits in DBKQ under this autoequivalence, as shifted by -2. But more formally, they are the same objects as those in DBKQ, just that we change the morphisms so that any two objects in the same orbit become isomorphic. And now the results by Bressler-Young says that if you pick a cluster tilting object, yeah.
I have a question. What is the conceptual significance of this -2?
Yes, that's a good question. So if you take this orbit category, now the Serre functor composed with -2 becomes naturally isomorphic to the identity, which means that the Serre functor becomes the second shift. And that's precisely what you need to get a 2 Calabi-Yau category. And it turns out to be important when you want to categorify cluster algebras to have 2 Calabi-Yau triangulated categories. So that's the reason for the -2. Yeah. So now pick a cluster tilting object in this cluster category and consider its endomorphism algebra lambda. And then what we remarked in the case A3 is always true. If you kill the ideal of morphisms that factor through an object in ad sigma t, then in ad t, you get a category of 2-term complexes of projectives up to homotopy. So their result is more general than that. They don't need acyclic quivers. They work with the quivers with potentials, so it's more general. But it's already quite interesting and surprising in that case. So now our aim is first, can we say more on this equivalence than being an additive equivalence? So CQ, the cluster category, is triangulated. So there are triangles somehow living on the left-hand side. And on the right-hand side, K-10 proj lambda is a full subcategory of a triangulated category, KB proj lambda. So there are some sort of triangles also on the right-hand side. So we would like to know if there are some more compatibilities between those two categories. I find this question quite intriguing, right? In representation theory, we're quite used to killing ideas of morphisms factoring through some class of objects. And here, it's slightly different. We want a class of morphisms that factor through two different classes of objects, but one class first and then the second. So we would like to understand why this specific question appears, and if there's a reason for this here, sigma t to t. And also, we would like to generalize the results to other settings that might be a bit similar. And one of those settings we would like to consider is Hillenbrug's Higgs categories, and that's the one we will consider in this talk.
Yann, can I ask you a question?
Yeah, of course.
This quotient that appears in the theorem is different from the quotient from the cluster category, right? So here you're taking the quotient, the objects are the same, but the homomorphisms are quotient spaces.
Yeah.
In the other cases, you are identifying objects.
You mean
my question is, what's the meaning of you say CQ modulo some morphism?
Yeah,
Meaning
yeah.
The objects of this category are the same as the object of the cluster category, right?
Yes, yes.
Home spaces are quotients.
Yeah, it's an ideal quotient. Yes.
And in the cluster category, you are identifying objects.
Yes, the formal construction of a cluster category gives the same objects as the derived category. You don't change the objects. You change the morphisms, right? The morphisms from X to Y are now let's say, the sum, direct sum of morphisms from any power of S minus 2 applied to X to Y, which makes two objects in the same orbit isomorphic.
Okay.
So it's, yeah. So it's not the same construction, you're right. We first take an orbit category and then an ideal quotient, but the objects are still the same.
See. Thank you.
Does it answer your question?
Yes, thank you. Yes.
Yeah, okay, good. Okay. So I will, next section, I will explain what are zero or slender extriangulated categories and why they arise in that setting. And then define Yilin-Wu's Higgs categories and describe the results we have in that case. So first, on the structures that are preserved by this additive equivalence. So recall that T is some specific object in the cluster category, some cluster tilting objects. And lambda is its endomorphism algebra, and we have this surprising additive equivalence. And it turns out that some of the triangles in the cluster category, so I'm now back to the example A3, some of those triangles in A3 are sent to triangles in KB proj of the form X, Y, Z to the shift of X. And in those triangles, X, Y, and Z are two-term complexes. They are all concentrated in degrees 0 and -1. And now we want to understand which triangles in the cluster category of type A3 are sent to triangles in KB proj. And those are precisely the triangles here, where epsilon is a morphism that factors through the additive category generated by the shift of the cluster tilting object T. So it factors through some summand of a sum of copies of sigma T. So we can define delta T to be the collection of all those triangles that satisfy this condition. And also consider the triangles in KB proj lambda, for which X, Y, and Z are two-term complexes. So I call delta the collection of those triangles. And what we observe in the case of the cluster category of type A3 is that the triangles in delta T are sent to triangles in delta by the additive equivalence. Now, it turns out that when we forget about the triangulated structure of the cluster category and only remember those triangles delta T, and when we consider the category K-1,0 proj lambda with those triangles in KB proj for which the first three terms are two-term complexes, then those two examples are instances of zero Auslander extriangulated categories. And so let's see what this means. So first, an extriangulated category is it's a generalization of both an exact category and a triangulated category. And the two examples that I've given before are examples of extriangulated categories that are examples you might keep in mind. So the cluster category with some of its triangles only, and the category of two-term complexes of projectives. So more formally, an extriangulated category is an additive category with a bi-additive functor from C up times C to the category of abelian groups. And this bifunctor is to be thought of as an X1 bifunctor. And we are also given an additive realization. I'll say a bit more on what this means, plus a few axioms. So those axioms are inspired from triangulated categories. And I'll say a word about those also. So the realization is here because so if you are in a triangulated category, there's an X1 bifunctor given by home to some objects, the homes from some objects to the shift of some other objects. So those are morphisms in that case. But if you're in an exact category, the X1 is given by equivalence classes of short exact sequences. So we want to generalize both those situations that look quite different a priori. And so instead of defining an X1 functor from a morphism space or from an equivalence class of short exact sequence, we are given a biadditive functor, and out of it, we get some sort of triangles or short exact sequences via the additive realization, S. So if delta is an element in the abelian group ECA, we think of delta as an extension between C and A. And the realization S will send delta to an equivalence class of a short sequence ABC. And the equivalence relation is the usual one, the one we would put on short exact sequences. So A and C are fixed, but we can change B via an isomorphism. And this situation will be written like this. So A, B, C, and delta is called an X triangle or a conflation. And the notation mixes the two cases of exact categories and triangulated categories. So it looks a bit like exact categories with the notations, inflations, deflations, or monomorphisms, epimorphism. And a bit like triangulated categories where delta sits on top of an arrow, except that now there's no shift. So I haven't written down sigma A on the right because there's no shift in an X triangulated category. And delta is an element in ECA, it's not a morphism. So the arrow is dashed to remember that delta is not a morphism. Okay, now the axioms of X triangulated category are inspired from those of triangulated category, and they say, for instance, that starting from two X triangles and a commutative square from one to the other, the commutative square can be completed to a morphism of X triangles. And there's an equivalent of the octahedral axiom that holds for X triangulated categories. Okay, I'm not going to be more precise than that, but I will give more examples. So any exact category is X triangulated, where the X triangles are the conflations or the admissible short exact sequences in the exact category. And the element delta is the element in X1 that is represented by the short exact sequence. So if you have a Frobenius exact category and you kill projective injectives in this category, you get a triangulated category. But if you only kill some projective injectives, you don't get a triangulated category. And more generally, if you take an exact category, which is not Frobenius, and kill some projective injectives, you don't get a triangulated category either. But in both cases, you still get an extriangulated category. So the conflations or admissible short exact sequences in the exact category give X triangles in the quotient. Now, triangulated categories are also extriangulated, and the X triangles are just the triangles where we forget about the shift. But also full subcategories of a triangulated category that are extension closed. So meaning that if you've got a triangle X, Y, Z with the end terms X and Z in the full subcategory, then the middle term has to be in the full subcategory. So those extension closed full subcategories are also extriangulated. And for example, that's the case of the homotopy category of two-term complexes of projectives. K-1, 0 proj lambda is closed under extensions in KB proj, which is triangulated. So K-1, 0 is extriangulated. And the X triangles in K-1, 0 are the triangles in KB proj, where the first three terms are in K-1, 0. So our complex is concentrated in degrees -1 and 0. And there's also a notion of relative extriangulated structure due to Herschen, Liu, and Nakaoka. An example of which is the cluster category with this structure delta T. So only some of the triangles. And those relative structures are obtained as follows. So we pick an extriangulated category and choose some additive subfunctor of the bifunctor E. So for instance, you could start from a triangulated category and look at some nice enough collection of triangles. And these are going to still be extriangulated. They will give an extriangulated category under a specific condition. So if you fixed a subfunctor of the bifunctor of extensions, that gives you, by taking the realizations of elements in that subfunctor, you get a specific class of X triangles, similarly to what happened for the class delta T of triangles. And so that gives a definition of inflations and deflations, the morphisms that appear at the beginning of such an X triangle or at the end of such an X triangle. And under the condition that inflations are closed under composition or deflation closed under composition, this gives an extriangulated structure. And that's precisely what happens for C and delta T. Okay, so with Mikhail Gorsky and Hiroyuki Nakaoka, we have defined a notion of zero Auslander extriangulated category. And it's defined as follows. So it has to satisfy two conditions. The first one is that every object has a projective resolution of length 1. So there is an X triangle P1 to P0 to X, where P0 and P1 are projective. In particular, the category has to be hereditary. And the second condition says that for every projective, there's an injective co-resolution of length 1, for which the first injective is also projective. This gives for every P an X triangle P to Q to I, where Q and I are injective and Q is also projective. And this condition is similar to asking for dominant dimension at least 1. So, as I said before, the category of two-term complexes of projectives is an example of a zero Auslander extriangulated category. And that's quite easy to check, so I'll explain quickly why. So first, we want every two-term complex of projective to be the cone of a morphism between two projectives. But by definition, it is the cone of the morphism between the projective that arise in degree 0 and the projective that arise in degree -1, now viewed as complexes concentrated in degree 0. So the cone of D is D itself. And for degree reasons, there are no morphisms from any complex concentrated in degree 0 to any shift of a two-term complex, right? If you take a complex concentrated in degrees 0 and -1 and you shift it, it becomes concentrated in degrees -2 and -1. And so there are no morphisms from a projective in degree 0 to such a complex. So this says that the projectives in degree 0 are projectives for this extriangulated structure. And so the triangle here shows that every object in K-10 proj lambda is the cone of a morphism between projectives. And the second condition comes from this triangle. So every projective P should arise in a triangle of the form P to Q to I, where Q is projective injective and I is injective. And here Q equals 0, which is obviously projective injective. And the cone is the shift of P. And again, it's easy to check for degree reasons only that the shifts, complexes of projectives concentrated in degree -1 are injectives in K-10 proj lambda. So that shows that the category is 0 Auslander. Now, the second example comes from cluster categories, but it can be stated slightly more generally. So if you take any K-linear triangulated category, which is home finite, so the morphism spaces are K vector spaces that are finite dimensional, and then pick an object T in C, and we say that this object is cluster tilting if first it is rigid, so there are no morphisms from T to its shift. And in particular, any triangle with n terms are in at T have to split. And it has also to satisfy the second condition here, which says that every object in the category has to be finitely presented with respect to at T. So there's a triangle T1 to T0 to X with T0, T1 in the additive category generated by T. Okay. So in that situation, we can also look at the class delta T, similarly to what we did for the cluster category of type A3. We forget some of the triangles and only remember those where the connecting morphism epsilon factors through ad sigma T. Yeah, there should be brackets around ad sigma T here. Epsilon belongs to the ideal of morphisms that factors through an object in ad sigma T. And then you obtain an extriangulated category by Herschen, the example I gave due to Herschen, Liu, and Nakaoka. So this is an extriangulated category, and it turns out to be 0 Auslander also. And the reason is the class delta T of triangle is precisely the class we have to look at if we want T to become projective. So triangulated categories do not have any projective objects apart from 0. But here we're looking at a relative substructure, which is extriangulated, but not triangulated, and you can have projective objects now. And why is T projective now? So let's pick any triangle, X, Y, Z, in delta T. So the morphism from Z to sigma X factors through ad sigma T. And pick any morphism from T to Z. Then the composition here has to be 0 because T is cluster tilting. So there are no non-zero morphisms from T to sigma of T. And by the axioms of triangulated categories, this means that there's a factorization here. And so T is projective with respect to the class delta T of triangles. Now, this is the definition of cluster tilting object, and you can see on the second point of the definition, the existence of those triangles T1 to T0 to X. Since T is now projective with respect to the relative extriangulated structure, this precisely gives a resolution of X by projectives T0 and T1. So that gives one of the two conditions for being zero Auslander. And the second one is similar to the case of K minus 1, 0 proj lambda. We have a triangle T to 0 to sigma T with connecting morphism the identity. And this gives the triangle P to Q to I that we are looking for. So this is also zero Auslander. Good. Now, our strategy or the idea we have to try and generalize Breussler-Young's result to Higgs categories is the following. First, so the curly T is the additive category generated by the cluster tilting object T. And this ideal that arises in Breussler-Young's results, morphisms that factor through some object in at sigma T, then in at T, it coincides precisely with the ideal of morphisms that factors through first some injective objects and then some projective objects for the relative extriangulated structure given by the class of triangles delta T. So that gives a meaning to these quotients now. And the second idea is things worked for cluster categories because with this relative structure, it becomes zero Auslander. So the, say, guess or conjecture would be that if you pick a zero Auslander extriangulated category and kill the ideal of morphisms factoring through an injective, then a projective, you get something which is equivalent to a category of two-term complexes of projectives, or more generally, K minus 1, 0 of some additive category, which I've called P overlined for some reasons you might guess. And this equivalence, we would like this equivalence to be an equivalence of extriangulated categories. So that's what motivated our paper, but we couldn't prove it in this wide generality, and we needed to add some restriction on the extriangulated category C. And I'll explain why a bit later. But at least we have this lemma that says that if you pick any extriangulated category, it doesn't have to be zero Auslander. And if you kill the morphism, the ideal of morphisms that factor through some injective, then some projective, it canonically inherits the extriangulated structure from C. So if you kill morphisms that factor both through an injective and through a projective, maybe with two different factorization, the bifunctor E descends to the quotients. Okay, because E doesn't see injectives nor projectives. So all the morphisms that would belong to this ideal compose to zero with an extension delta. But then you want to check if the axioms are satisfied. And it's not always the case if you kill this ideal of morphisms that factor through an injective and through a projective. But if you want one factorization that goes via an injective first and a projective next, then the axioms are satisfied. So it's somehow the best quotient you could take so that the extriangulated structure on C immediately gives an extriangulated structure on the ideal quotients. And that somehow explains why it's this ideal sigma T to T that arises in Breussler-Young's results. So that answers one of our aims. And now we want to relate this zero Auslander extriangulated category to a category of two-term complexes. And the naive idea for doing this is the following. Pick an object X in the extriangulated category and fix, for each object, fix a projective presentation. So an X triangle P1 to P0 to X. And you could naively send X to its projective presentation. That would, yeah, be the first idea you could have. And it sadly doesn't work that easily because of issues with functoriality. So doing this naive construction is hard to make functorial. So our answer to this issue was to look at DG enhancements where things work better. And that works for Higgs categories. So let me explain or define Higgs categories. So the whole story started with the acyclic cluster categories introduced by Brandmarsh, Reinecker-Rayten, and Turdorov. And there was a first generalization due to Claire Amiot, where you could replace the acyclic quiver Q by a quiver that might be cyclic and that might have cycles, but then you should pick a potential. So this means picking specific relations in the quiver that have a very nice shape, then can be described using something called a potential. And then it was further generalized by Yi-Lin Wu to the case of relative cluster categories, where you not only take a quiver with potential, but you also take some frozen parts in your quiver. So frozen vertices and frozen rows. And the aim by taking relative cluster categories is to not only categorify skew-symmetric cluster algebras without coefficients, like Amiot's cluster categories do, but also skew-symmetric cluster algebras with coefficients. So the frozen part is here to deal with the coefficients in the cluster algebra. So let me explain this a bit more. So start from QFW. So Q is a quiver with no loops, no two cycles. F is a frozen part of Q, which means it's a sub-quiver, not necessarily full. So we pick some vertices, call them frozen vertices. They're in F, and some of the arrows between the frozen vertices. And then W is a potential, which means it's a linear combination of cycles in the quiver Q. So here's an example of a frozen quiver where the potential is 0 because there's no cycle in that quiver in that case. And the frozen part is made out of 3 vertices that are circled by a box. And we take no frozen arrows in this example. And so starting from Q, F, and W, Yi-Lin Wu generalizes the construction of a Ginzburg DG algebra and calls it a relative Ginzburg DGA. And it works as follows. So for every arrow alpha in Q1, which is not frozen, you add an arrow in opposite direction, alpha star. And here, all the arrows in this example are unfrozen. They are not frozen, so you will get an arrow in opposite direction for each of the arrows in Q1. Then also add loops at the unfrozen vertices. And the loop at vertex I is called Ti. And looking at the path algebra of that quiver will give an algebra, but you will want it to be graded differential with the differential. So the grading comes from the grading on the arrows. The arrows in Q1, in Q, are all of degree 0. The arrows that have been added in the opposite direction are of degree -1 and the loops of degree -2. And the differential of the DGA is defined on the generators by d of alpha star is the partial derivative of the potential at alpha. So the partial derivative at alpha is linear. It sends a cycle where alpha does not appear to 0. And if alpha appears in a cycle, you just rotate it so that alpha appears first, erase alpha, and keep what remains. And that's the partial derivative with respect to alpha. And the differential at Ti is given by pre-projective relations. So you take the sum of the commutators alpha by alpha between alpha and alpha star for every arrow alpha that starts at vertex I. Okay. So whatever the definition is, it gives a nice DG algebra. Yes?
Sorry, can you repeat the definition of the potential W?
Yeah, I'm being a bit sloppy here. I said it's a linear combination of cycles.
What cycles?
But then, oh yeah, so in the example, W is 0.
In what example? In this example, it's 0?
Yes, yes.
Ah.
The quiver Q that corresponds to the arrows, the straight arrows in black, has no cycles. So,
so that's the potential that already appeared before.
Yes, yes.
Ah, okay, sorry. Okay, thank you. Okay, I understand. Thank you.
Okay. So in short, starting from Q, F, and W, you can construct a DG algebra that generalizes Ginzburg DG algebra of the quiver with potential. Okay. And now there's a definition that was due to Cléramio in the unfrozen case, where you only have Q and W, and generalized by Yilin Wu to the case of where there is a frozen part. And I will, in the remaining of the talk, I will always assume that H0 of gamma of the Ginzburg DGA is a finite dimensional algebra. And I will denote E sub F, the sum of the idempotents at the frozen vertices. And gamma bar is going to be the quotient of gamma by the ideal generated by this frozen idempotence, which turns out to be isomorphic to the usual Ginzburg DGA associated with the unfrozen parts, Q bar, W bar. So Q bar, W bar are obtained from QW by erasing all frozen vertices and their adjacent arrows. So if a cycle in W goes through a frozen vertex, then it's sent to 0, and you don't keep it in W bar. We have to look at the perfect derived category of gamma. So it's the smallest triangulated full subcategory of the derived category of gamma that contains gamma and is stable under taking some ends. So it's called a thick subcategory. And the perfectly valued derived category of gamma bar is the subcategory of the derived category of gamma bar given by the DG gamma bar modules, which have finite dimensional total cohomology. Okay. And now the relative cluster category is a Verdier quotient of per gamma by PVD gamma bar. So Yilin Wu had to prove first that PVD gamma bar is included as a triangulated subcategory of pair gamma, and then take the Verdier quotient. And this Verdier quotient is the relative cluster category constructed from Q, F, and W. So the advantage of this construction over the orbit category construction is that it's now obvious that what you get is triangulated. It was difficult to prove it for orbit categories, but it's obvious for Verdier quotients. And if Q is an acyclic quiver with no frozen parts and W 0, this construction recovers the usual acyclic cluster category that was proven by Claire Amiot in that case. Okay. Now this relative cluster category per gamma over PVD gamma bar does not categorify cluster algebra with coefficients. You need to look at some subcategory of it. And the subcategory is taken as follows. So the relative cluster category is a quotient of per gamma. And inside per of gamma, we look at some full subcategory, which is chosen for the following reason. So if we want to categorify a cluster algebra, we want cluster tilting objects. And in particular, we would like gamma to be a cluster tilting object. And one of the conditions for being cluster tilting is every object should be the cone of a morphism in add gamma, or should be an extension of an object in add gamma and an object in add sigma gamma. So this condition is written down gamma star sigma gamma. So gamma star sigma gamma is the full subcategory of per gamma of all objects that are an extension of an object in gamma, in add gamma, and an object in add sigma gamma. So we restrict to that subcategories. And then we also want the frozen vertices to correspond to coefficients. And so they should behave in the categorification, they should behave like projective injectives. So we want to make gamma EF projective injective. And so we look at it X1 orthogonal and intersect it with gamma star sigma gamma. And then take the image of this fundamental domain inside the relative cluster category. And that's HQWF. And that's what Yann Palu defines as being the Higgs category. And that's what's going to categorify a cluster algebra with coefficients. Okay. So, yeah, so the fundamental domain is some X1 perp intersected with gamma star sigma gamma. And we're going to use this to show Brusler-Young's results for Higgs categories. And yeah, so Yann Palu proves that the Higgs category is it's extension closed in the relative cluster category, so it is extriangulated, and it's also Frobenius extriangulated. So you could mimic the definition of a Frobenius exact category, but replacing conflations by X triangles, and you would get the definition of a Frobenius exact category. So it has enough projectives, enough injectives, and they coincide. Projective injectives coincide. In that case, the quotient by projective injectives give a triangulated category. Here, the projective injectives are precisely given by add gamma EF, which is good. We wanted gamma EF to become projective injective to play the role of the coefficients. In the stable category, the quotient of H by add gamma EF gives, as a triangulated category, the usual Amiot's cluster category associated with the unfrozen parts. And moreover, the image of gamma sent to in H, in the Higgs category, is a cluster tilting object. So this situation is quite nice. The Higgs category behaves a bit like a cluster category, except that it's now extriangulated rather than triangulated. So our main results now, so we pick an abstract situation that looks like the situation of the definition of the Higgs category. We take a non-positively graded DG category, which could, for example, be the relative Ginzburg DG algebra, viewed as the DG category, and a full subcategory, which has to satisfy some technical finiteness conditions. So there has to be approximations, left approximations by E in the perfect derived category of A. So that's what's called being covariantly finite. And this full subcategory E would be in the example where A is the Ginzburg DG algebra gamma, E would be add of gamma EF. And our theorem, main results say that if we define HE tilde to be the X1 orthogonal to E intersected with A star sigma A inside the perfect derived category of A, so that mimics the construction of the fundamental domain for the Higgs category, then what you get is a zero Epsilon extriangulated category. We can describe its projectives. They are just given by A inside its perfect derived category. We can also describe its injectives in terms of Bongard's co-completions. And we get a full dense extriangulated functor from this H tilde E to some category of two-term complexes of projectives. So the algebra we have to look at is the quotient of H0A by H0E. Well, and the kernel we get for this full and dense functor is precisely the idea of morphisms that factor through an injective first and then a projective. Well, that result looks a lot like what we wanted, and we can apply it to the case where A is the relative Ginzburg DG algebra to obtain the following corollary. So if we let T be the image of gamma in the Higgs category, and I write H sub T for H with the relative extriangulated structure that makes T projective. So that's the extriangulated analog of delta T that appeared for cluster categories. So we only keep the X triangles for which T is projective. Then the fundamental domain is equivalent as an extriangulated category to the Higgs category with this related extriangulated structure, HT. And so we can apply the previous theorem on DG categories to obtain a full dense extriangulated functor from the Higgs category to K-1,0 proj of the usual Jacobian algebra. So it's H0 of gamma bar. And the kernel is precisely the morphisms that factor through an injective, then a projective. And so if we take the quotient, we obtain an extriangulated equivalence between HT mods injective to projectives and K-1,0 proj of some algebra. So that recovers and generalizes Brüssler-Young's results with the additions we wanted. So first, we understand the quotient we're taking. So this sigma T to T that appeared in Brüssler-Young's result is injectives to projectives. And that's the quotient you want to take if you want to remain extriangulated. And second, the additive equivalence is now an extriangulated equivalence. So we are remembering the extra structure on both sides. And finally, it works for Higgs categories and not only cluster categories. And let me finish with the first example we looked at of a cluster category of type A3, where we had a cluster tilting object with the endomorphism algebra was the 3-cycle with radical square 0. You can obtain it from a quiver with potential, the potential being the 3-cycle. And there, what you obtain is a self-injective algebra. And if you specialize the previous corollary to the case of a self-injective algebra, take no frozen parts, so F is empty, and consider the Jacobian algebra, H0 of gamma, of the Ginzburg DG algebra. So we've assumed that it was finite dimensional, but we assume now, moreover, that it is a self-injective algebra. So in that case, there are no morphisms from sigma T to T, or from injectives to projectives. And so the extriangulated equivalence we obtain does not need to take the quotients, projectives to injectives. So we get an extriangulated equivalence between the cluster category, CQW, and the category of two-term complexes of projectives. But now the cluster category is with the relative extriangulated structure, making T projective. That explains the first example we had where we didn't need to take any quotients. And thank you for your attention.
Thank you, Yann. Let's unmute ourselves and give the speaker a round of applause. Okay. If you have any questions for Yann, you can ask them now. So I had just not exactly a question. So this relative cluster category, how easy it is to track generation properties of it?
So what sort of properties do you want?
I mean, it's a triangulated category, right? So do we know what the, like, is it compactly generated? Do we know the generators?
Yeah, I think it's, I don't know well enough to answer that question, sorry. But so it's a quotient of the perfect derived category. So I guess it's still compactly generated, probably.
Mm-hmm. Yeah. Well, I mean, I would love to ask the same questions for the analog, for the Higgs category analogs, but I don't know Higgs categories well enough to even formulate that question properly in that context.
Yes, I don't think there is a definition of compact generation for extriangulated categories yet. So I wouldn't even know how to define it for the moment.
Okay. Yeah, thank you. Any other questions or comments?
So Yann, the fact is that zero Auslander, it refers to the projective injective appearing in the definition of X triangles of delta, and is it enough to describe all the interesting like categories, or you are planning to generalize to one Auslander, or maybe there is no need because with this notion you can cover all the interesting examples.
Can I say, Giovanni?
Yes.
I think my internet dropped for 2 seconds.
So sorry, I asked about higher Auslander extriangulated categories.
Yeah, no, that's a very good question.
If it makes sense to consider them. And
so the zero in zero Auslander comes from the fact that it's global dimension at most 1 and dominant dimension at least 1. So you could ask global dimension at most n, dominant dimension at least n, and define that to be n Auslander somehow. So we only looked at zero Auslander in the paper with Misha and Hiroyuki, where we defined zero Auslander extriangulated categories, because we were interested in mutations of rigid objects. And all the cases of all the examples we had in mind were zero Auslander. So that worked well there. And then if you want n Auslander, you're probably more looking into higher homological algebra or higher AR theory. And the proper setting is probably n exangulated categories rather than extriangulated categories.
Yeah, of course.
But both make sense. You could look at n Auslander extriangulated categories or n Auslander n exangulated categories. That I think both make sense. And so Xiaofa Chen proved a form of zero Auslander correspondence that mimics, well, mimics. That's an analog of Auslander-Iyama's Auslander correspondence. I mean, Auslander-Iyama's correspondence, but for d equals 0. And he did that using exact DG categories. So they form an enhancement of extriangulated categories. And I'm not sure where it is, where it stands at the moment, but he's planning to do some D Auslander correspondence also. So for exact DG categories.
Okay. Mm-hmm.
So there's a work in progress at least on the D Auslander case.
Thank you. Any other questions, anyone, or comments?
Hi.
Hi, Mindy.
Hi, I'm Mindy. Sorry, I have the question about the subcategory of complexes concentrated in some rank. Mm-hmm. For example, if you change complexes concentrated from -1 to 0 by complexes concentrated from -2 to 0, that subcategory is again extriangulated category?
Yes, yeah, it's still extriangulated. But then it would be an example of if I'm not wrong, it should be an example of a one Auslander extriangulated category.
Thank you.
Yeah.
Thank you, Mindy. Any other questions, anyone? Anything in the chat? Okay, I don't think there's anything in the chat now. Okay, in that case, let's thank Yann once again. Yeah, I think one of your co-authors did manage to come at some point.
Oh,
I think
good.
Mikhail Gorsky was here for a bit.
Okay.
Yeah. Okay, yeah, thank you.
Thank you.
We are supposed to have a talk next week by Leo Alonso. But yeah, I'll send out the abstract when I get it. Okay, stop recording now.